Hi everyone, so my name is Louis and today I'm going to present our work, Approximate Bayesian Computation with Domain Expert in the Loop. And this is joint work with my colleagues from the Department of Computer Science at Aalto University in Finland, Ayush, Bharti and Kaski. So today we're going to talk about likelihood-free inference, and the goal of likelihood-free inference is to infer some model parameters given some observations, but in the scenario where the likelihood is intractable, that is, that the likelihood cannot be evaluated numerically, and this arises in fields like genetics, ecology, cosmology, and so on. And as a result of this, the classical estimation or inference techniques cannot be applied. But the one thing that we can do is that it's possible to simulate or sample from the model for any given value of the parameter theta. All right, and so one of the methodology that we have in likelihood-free inference is called Approximate Bayesian Computation, or ABC. And the goal would be to characterize the posterior distribution of the parameters theta, but ABC permits sampling from an approximate posterior distribution. And so in ABC, we have this basic rejection ABC algorithm that is described in this ABC. Then we will sample from an approximate posterior distribution, which is an approximation of the real posterior distribution. And then it works like this in this little block. Then first we sample from the prior distribution, and then we simulate a data set from the model given this value of the parameter. And then we need to compare if this artificial data set that we obtain looks like the true observations that we have. And one way to do this is to use summary statistics. And we are going to compare if the summary statistics on the observed data and on the artificial data are, let's say, close enough, right? And if that's the case, then we are going to accept this parameter sample. And basically, so this is a rejection algorithm, and you are going to repeat this until you have, let's say, reached a certain number of samples, and these accepted samples are IID from this approximate posterior distribution. So the whole ABC methodology requires choosing several things. First of all, this distance metric, rho, then these summarizing functions, or as I was saying before, this summary statistics that you use to summarize the data, S, and the threshold epsilon. And today we are going to focus on the choice of this summary statistics, which is crucial to the performance of the ABC method. And yeah, choosing these summary statistics is critical, and it's also non-trivial because, first of all, in most models, you cannot find sufficient statistics, and then you need to navigate a trade-off between information loss due to summarization and the curse of dimensionality. And one way out of this situation is to bring in domain knowledge, and especially domain knowledge from experts. And usually practitioners will, have this tedious trial and error process to construct the appropriate summary statistics for the problem at hand. And some methods have been proposed in the literature to find, given a pool of candidate statistics, to find, let's say, the best one or the desired one. So you have subset selection methods, projection techniques, or regression adjustments, for example. But all of these methods fail, or let's say the performance degrade in two scenarios. The first scenario is when the number of available simulation is limited, what we call low simulation regime. So that is when we have a simulation budget, which is quite limited, or when the model is misspecified. That is when the true mechanism generating the data does not belong to the family of model that we are studying. And in this work, we have proposed this human in the loop ABC method. So we propose a human in the loop ABC statistic selection from a pool, as I was saying before, which considerably eases the work of domain expert. And by bringing them into the inference loop, we are able to achieve better posterior characterization in these two scenarios I was talking just before. So when the model evaluation is costly, that is when the budget for simulation is limited, or when the model is misspecified. And we work with the assumption that the knowledge of the expert is tacit. So if you take a look at this little figure, it means that the domain expert has some tacit knowledge about what are good statistics to use, but this knowledge needs to be elicited. And so we have put some kind of experimental design or active learning method to elicit this knowledge, and we are going to sequentially propose to the expert some statistics that we think would be useful to include in the model, and showing the expert, let's say, the evolution of the ABC posterior given the inclusion of the statistic. And based on this information, the expert is able to say, let's say, yes or no. It's a binary feedback model, and we integrate this feedback into the model to, say, converge to an optimal subset of statistics. And now I'm going to describe some results briefly. So this is the results in this low simulation regime. We study this model called the GNK model, which has 4 parameters to infer, and we have constructed a pool of 15 statistics, but only 4 out of these 15 are, let's say, informative. And what you can see on these plots is that when the budget of simulation is limited, when we outperform all the other methods, and as the budget of simulation increases, then the performance of all methods starts to be basically the same. And so when the budget of simulation is limited, then it's compensated by this expert's feedback, this additional information that we can bring into the model. And some results about misspecification. So in this case, we were studying a radio propagation model. And one assumption that we have is that the expert is also able to detect misspecified statistics when they are presented some inference results. And the results here are given with these plots. And we have this parameter zeta, which specifies the misspecification level. And when zeta is equal to 0, that means there is no misspecification. So that's on the left, panel A. And in this case, the performance of, let's say, standard ABC and human in the loop ABC is the same, but as the misspecification increases, so you go to panel B and panel C, then the performance of the classical ABC quickly degrades, whereas our human in the loop ABC remains relatively robust to this misspecification. And that's because the human expert has been brought in and was able to detect this misspecification. So some take-home messages. So we introduced the first ABC method that actively leverages domain knowledge from experts in order to select summary statistics, again, from a pool. And it involves fairly limited effort from the expert because the expert only has to give binary feedback, yes or no, and present it with only a few statistics. And we show that we are able to outperform regression ABC in situations where the simulation budget is limited. And as I was saying just before, involving the expert also gives us the opportunity to detect misspecified models, which is something that is the current method could not do. So yeah, thank you very much for your attention. Sorry again with this slide mix-up. And if you have a question,
thank you very much.
I'd be happy to answer.
Thank you.